This is going to what we are going to discuss now. And that the thermodynamic enhancement factor can be from 1 to 10,000. So in a superionic conductors, for example, the thermodynamic factor can reach the value 10,000, which is really different from the normal self-diffusion coefficient. Okay, so the W, thermodynamic enhancement factor, we see the Ji is going to be Bi over round x over round mu I, okay? And that is going to be Bi over Kt round ln Ai over round x, okay? Since round the derivative of log is going to be something like this, so that from here we can set the concentration can be related with this equation. It's just a simple mathematical manipulation. And then the Ji is going to be Bi Kt and round ln Ai over round ln concentration round concentration over round x. And this term is the self-diffusion coefficient, okay? And activity coefficient relates the concentration and activities, and we said gamma I is not a function of concentration, okay, and the Henry's law is applied, then this term is going to be 1. Okay, so First law says Ji is equal to chemical diffusion coefficient and concentration gradient. Here, this is a chemical diffusion coefficient, right? So now the chemical diffusion coefficient is going to be related to the self-diffusion coefficient by the thermodynamic enhancement factor, which is activity and concentration. And this is going to be called thermodynamic enhancement factor. It is often called in the metallurgist Dawkins thermodynamic factor. That is 1 plus round gamma I over round ln. Okay. And non-Einstein equations. Let me mention about the Einstein relations. Now, if we have electric potential gradient only, no chemical gradient. What does this mean? We are in equilibrium. Right? Say we have a situation like this, and the Ji is particle flux density, is again the particles per centimeter square in a reference plane for the time. And now the current density, charge flux, density. Now, this is nothing but the particle GIQ, the charges each particle can have, and there's a particle flux. And Ohm's law says potential is going to be IR, or volts, amps, and ohm in terms of the unit. And the current is equal to phi over round x. That is the field, and there's a volt per centimeter and ohm centimeter, so that volt for ohm centimeter square, that is amps per centimeter square. I total sigma I And if we write down this equation in terms of the conductivity, then we are going to have an equation something like this. Here, sigma I is going to be partial conductivity, and so that the total conductivity is going to be the summation of all partial conductivities, and this conductivity is Ti, where Ti Ti is transverse number. Transverse number of species I. There is a fraction of current density by species I. Now, Ji is Bi here. I over Q square I. Total and sigma, we do not have a sigma total, sigma Ti, transverse number. So actually we have to write down sigma T, Ti, something like this, okay? And then Einstein relations says DSI self-diffusion coefficient of species I is going to be Bi KT, so that the self-diffusion coefficient of species I now is going to be sigma T Ti transverse number KT over GIQ square and then concentration. And this is going to be called Nernst-Einstein equation. Nernst-Einstein equation relations. So the real meaning of Nernst-Einstein equation or relationship is that we want to relate the diffusion coefficient and the conductivity of the material. Both two are kinetic parameters, moving of the particles inside the material. How fast it can move, okay? And this should be somehow related. And then this Nernst-Einstein relation says we can convert any time the chemical diffusion coefficient with the conductivity through these relations. Okay, next week on Monday, we really try to discuss about the techniques, electrochemical techniques to determine the kinetic parameters, the diffusion coefficients, and other things. Okay, I'll see you next week.